to every element of a list or array, however you want to think about this. Java does not have a good way of doing list comprehensions. C++11 recently introduced this concept of allowing you to do these things with list comprehension. For each, the for each concept is the closest that we've gotten to in any other language. So like if you're looking at, say, for example, C++11, for each is the concept that they use for list comprehensions. It's still not exactly a list comprehension, but it's pretty close. The idea is that for each element of a list, or each element of an array, or each element of a collection, you're going to apply a function or a set of functions to that. C# actually does list comprehensions fairly well. They have an entire subpackage called link, L-I-N-Q. Link is exceptionally powerful, and it adds a whole bunch of this functional programming stuff to it. Python builds it in by default, so that's what we're going to be looking at, is Python's list comprehension. The simplest list comprehension is what we were looking at before, where you essentially ask for, you would essentially do, or you write a command. For example, I have a list with let's before we do an example one, let's do go over explicitly what we're doing. Let's suppose we have this list. We have the list 1, 2, 3, 4. If I want to apply the function monkeys, let's say we have a function called monkeys. That function takes a single argument x and does something to it. Returns a value, or prints that x, or does something to that x. Typically, we want to think about the functions that will return value. Let's suppose that the function monkeys returns x times 2. And so if we were looking at this as a Python function, it would look like that. Using the terminology that we've done, or the examples that we've done, not necessarily just in Python, but the way we know how to do this, how do we apply monkeys to each one of these elements of the list? Some kind of loop. So go ahead and take a second and write the for loop that would apply that function monkeys to this loop, to every element of this list, and then see if you can figure out how to make it so that you would make a new list of the returned result. So for example, the new list should look something like 1 times 2 is going to be 2, 4, 6, and 8. That's a terrible bracket. So the new list would look something like this. So go ahead and give it a second, see if you can come up with something that'll do that. And then we'll look at how to do this in both the for loop and the list comprehension fashion. All right, does anyone have a for loop that would do this? If you want to, we can assume that we have x is the first list. How would we write a for loop that would go through and apply monkeys to each one of those?
For I in x.
So when we say for I in x in Python, how is this different than the traditional for loops that we're doing in other languages? In other languages, when we use the I variable, usually the I stands for index. Does I mean index here? No. It actually means whatever the actual value is here inside of the list. So it's not bad to use I, but still typically it's not really an I here. So I'm going to use a V, lowercase v instead of I. And this is going to be for value. It's just personal preference, how about I think about things. If you don't think about it that way, use I everywhere. I still use I when I do this personally, but as good practice, let's say V for value as opposed to I for index. But otherwise, okay, good. Okay, what?
I forgot to do something. First, say x2 equal bracket.
So x2 is some other bracket, some other list, some empty list.
And then inside the for loop, it's x2 dot append monkeys of, what do you call it?
Of V for value. Like so. So you use I instead of value here, right? So in this case here, you know about the append function on lists that will append a list. If you didn't know about the append function, you could say something like this as well. This would be the equivalent. You could say for V in X, X2 equals X2 plus the list of monkeys of value as well. Those are equivalent lists. Python allows you to concatenate two lists together, like so. It'll take the two lists and concatenate them at the bottom. So the x2 is a list itself. We concatenate in the extra monkeys value, and that'll concatenate the list together to create a new list instead of using append. This is much faster than this. This here modifies the actual list data structure. This one down here creates a brand new list data structure, copies over every element from each of them, and reassigns it to the value. So if you had, say, for example, 10 million elements, this one would be pretty quick. This one would be painfully slow. Unless there's some optimization where Python figured this out, and I don't know if Python 3 has that optimization or not. The example of doing the equivalent thing as a list comprehension, instead of the two for loops, is going to be the following. Like so. Or we could have something slightly different. So if that doesn't quite make sense yet, let me make it into two different steps. So this would be, for example, x2 equals that. This is our second list equals that. Let's take a look at it in a different form. So x equals the original list, 1, 2, 3, and 4. x2 becomes a list comprehension of that previous list. Like so. Let's take a look at all the different parts in this list comprehension for what we're doing. How many different parts do you see so far? So these two things should be new to most of you in terms of looking at the structure. There's 3 sections, more or less, in each of these. The 3 sections would be this part here, this here, that here, which would be the same 3 sections down here. What are we doing in this first chunk here? So this is this is the function to be called, or the function that we're going to be calling on V here. This is the function to apply. What's this middle section doing here?
Defining the name of the variable that it's going to be sending the function.
So defining the name of the variable for this function call over here. What's this part over here? List of original data. Original data. List of original data. Let's go ahead and take a look at this in practice. Okay. So I've implemented the way we did before, the way I did before with the two lists, and we'll look at the append as well. We're going to do the run here. And if we would take a look at x2, x2 is the list 2, 4, 6, 8, the same way we had it over there. If we take a look at x, it's still the 1, 2, 3, 4. If we use the append method, as opposed to, we can see that x2 is the value that we're looking at. Instead of saying x is going to be 1, 2, 3, let's go and say range from 1 to, let's say, 1,000,000, like so. Using the append method, it finishes over there, and if I go, it finishes running, and if I use the x2, it's probably going to die because it's trying to print 1,000,000 elements into my web page. So we're going to refresh that. Oh, yep, and we're dead. Okay, well, while that sits there and figures out if it's going to refresh or what it's going to do over here, let's take a look at some examples of some Python list comprehensions. So for example, let's suppose we have S, V, and M. S is going to be the list comprehension of x star star. Star star means exponentiate or exponent instead of multiply. For x in range from 1 to 10, so for example, x 0, for the range of 10, what does range of 10 give us? Does anyone remember? Is that going to give us 0 or 1 to start with? Kill that? I don't know if I can kill that. Let's see what range of 10 gives us if I try to print all those things. For x in range of 10, I don't remember if it gives us the 10 or not. The 1 or not. 0, so it does start at 0. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, so on and so forth. We can see where the function that we're applying is x squared, is what we're doing here. For x is in the range from 0 to 10, so then we get all the way up to 9. So 9 squared. The second one is going to be 2 to the power of I, for I is a range of 13. So for example, 2 to the 0 is 1, 2 to the 1 is 1, 2 to the 2 is 4, 2 to the 3 is 8, 16, 32, you can see all the way, there's all the powers of 2. M is a little bit of an extension. The list of the data that we have can be filtered. So for example, we're going to say for x in this S. And so S is our original set, which is this guy down here. We can filter it with an if statement inside here. If x mod 2 is equal to 0. That's going to be the even elements of that. And so you can see that what we do is we took just the even elements from S. 0 is apparently even, well, 0 mod 2, it's not just necessarily even. Even is both. I don't know. Yeah. 0 is even. Any questions about those guys there? And how we did that? This is exceptionally powerful because you can do these kind of things in lots of places. If you want to be able to generate a large number of elements that follow some sort of pattern, you can easily do that. So for example, if I want all the powers of 2, I don't have to write a function that generates powers of 2. I can just have a list comprehension that gives me the powers of 2. What's the other benefit, or what's the other thing that's important about this here? What's important about this list comprehension?
Extremely powerful comparisons.
Sorry?
You can do comparisons.
We can do comparisons on the data outside of it, yeah, so we can filter the input data to it.
It's terse.
It's very short, which makes it easier to write complicated things on a single sentence, on a single line, so you can do a lot of work in a short period of time. It makes your code easier to read. So for example, if you wanted to have all the powers of 2 up to 4096 kind of deal, here's a line of code that would give you all the powers of 2 up to 4096. And if we wrote it like that, doesn't like me.
You turn it to
And then I put my comment here. Is it easy for me to, well, it might be easy depending on how comfortable you are with list comprehensions. Is it easy to see that that line of code is a list comprehension that gives you all the powers of 2 up to 4096? It might not be straightforward, but then you have that comment that tells you that it's all the powers of 2 up to 4096, and you can go like, okay, I don't have to write a bunch of code, and so this isn't going to clutter the rest of my program. So my program can become shorter by it being terse. The other part of it is, does it matter, for example, if I calculate 64 before I calculate 8? They're independent, so they don't depend on each other. I can technically do each one of these in parallel with each other. This is that concept of independency we talked about last week when we were talking about functional programming. When you have functions that are independent of each other, you gain the ability to do them simultaneously. The PlayStation 3 was an interesting hardware machine. Sorry. It was an interesting piece of hardware. Some universities bought a bunch of PlayStation 3s and did what with them? Does anyone know? They clustered them. They used the processors, and they used 6 of the processors in them. They didn't use the regular processor. They did, but they didn't really use the regular processor. Why did they cluster them? What did they build with those clustered PlayStation 3s? Supercomputers. How do we build supercomputers out of PlayStation 3s? And what does it mean? That's the question, is what is a supercomputer? And so the answer is a supercomputer is a computer that is capable of doing lots and lots of calculations simultaneously. That's why we talk about the teraflops, gigaflops, petaflops. I don't even know what the fastest computers are right now. What are the fastest computers? Fastest supercomputer. Maybe they keep track of them. What do we got? 33.86 petaflops. That's a lot. That's 1 petaflop is 1 quadrillion floating point calculations per second. This is only useful if you can do this. If your data is not what we call vector, is not vectorizable, or you can't vectorize your data in this way that you can apply the same function to every piece of data. It doesn't matter how many calculations per second you can do, because you're going to be stuck doing things in a linear fashion. So for example, when you write your line, or when you write a line of code like this, let's write the same powers of 2 here, iterative power 2, we'll call this IPT, IP2. So iterative powers of 2, for I in range of 13, IP2 dot append to the I used index, it doesn't matter. Is it actually, this is the index system? This for loop here, how many instructions am I doing at one time? One instruction at a time. So I start with the first I say I equals 0, I do everything inside the for loop. Then I say I equals 1, and I do everything inside the for loop. If I put multiple things inside the for loop, I have another instruction here, another instruction, so on and so forth. I do line 8, then I do line 9, then I do line 10, then I do line 11, then 12, then 13, then 14. And then I start over again. But I can only do one instruction at a time. Supercomputers are only able to achieve those very high flop numbers, petaflop numbers, if everything everything can happen in parallel. Does anyone have an example of something that's in pretty much every computer today that does this for us? Graphics cards. We talk about 3D games. We talk about watching movies. Have you guys heard of H.264 and H.265? Those kind of video technologies. You want to watch DVD quality movies, you use H.264, H.265. Those things are built on vectorized components. So H.264 is, as an example, H.264 and H.265 are very good video encoding techniques in the sense that they get good reduction in bandwidth required to transmit a movie, but you have relatively high restored quality. But you also are able to do them in parallel. So for example, if you're doing H.264, and if you want to get into video theory, if you have an entire video screen, you can do sections of the video simultaneously. They're independent of each other. And so you can have your video card render the entire frame almost instantaneously without having to do multiple steps. This is more true with the new ones, H.265 and VP9. I believe it's called VP9. This is Google's one, which they also call Dash. Lots of names. But all of these things rely upon the concept of being able to do things in parallel. So being able to think about this list as independent of each other. Yes?
Do those operate per pixel, or do they operate in like groups of pixels?
Both. They operate on groups of pixels, and then within them they operate per pixel. If you want to understand how and why, look up JPEG. JPEG's the simplest thing to do, and they do blocks of pixels that then can be single pixel done. That's the way you want to think. That's the easiest one to look at is JPEG. Once you understand how JPEG works, then you can look up how MPEG works, and then once you understand how MPEG works, then nothing H.264 and VP9 still don't make any sense. Yeah, magic. That's good. But this is the motivation for learning how to do these things. As an example, this function here that is many steps in a row, 8, 9, 10, 11, 12, 13, 14, 12 may or may not depend on 9, as an example. If line 12 depends on line 9, it is difficult for this to be vectorized such that I can do each step independent of the other step, because they're dependent upon each other. The goal is to figure out if if they can be independent or they can be dependent on each other. That's one of the big steps with doing list comprehensions. So let's see. There's a function called upper. So that's all capitals. If I type in upper on a string like hello in Python, oops, not upper. Is it 2 upper? Hold on. Let me cheat real quick. Oh, it's just the word. Okay. So if you take the word hello, for example, and you say upper on it, it'll uppercase hello. And if you take the word hello with a capital E, I don't know, whatever, like so, you call lower on it, it'll lowercase it. And if you pass the length, if you pass them to the length function like so, you can get the length of a word. Let's suppose that you have a sentence. Can you figure out the length of every element in that sentence in a single line of Python? Let's suppose we get a sentence. So if I give you the sentence, send equals the sentence, hello, how are you? Like so. And assume that the question mark is part of the word you. I want you to tell me how long each one of those words are. What's the length of each one of those words? See if you can write a list comprehension that'll do that for you. Freeze this for a second. Let's see if it. All right, does anyone have a solution? Kinda? We're going to run this so we get that over there. What do you got? Oh, you're testing though. I was trying to. So it's okay.
I'm not running it.
So does it? So you haven't tried it yet?
No, I don't even know how to finish it.
Okay, good. What do you got?
So far, I have whatever variable. I guess you wouldn't even need to put a variable in there. You just put it in brackets, len, and then in parentheses v, for v in, and then the string that you want, dot split.
So let's do just this one before we do the dot split there. What is sen? Sen is the sentence that we have here. If we say for v in sen and we do the length of that, we get 1 each time. What is this 1 representing in each case here for each one of these things in sen? Each character. Good. So if I put the split on here, does that give me the length of the words? No?
It includes the
I said include the question mark on the thing. If you wanted to, you could actually do a replacement. I don't remember how to do it exactly in Python. Let's do a quick Google search. Remove punctuation Python. Remove punctuation Python. Strip punctuation. Strip command will do it. punctuation. So here's an example of a list comprehension on how to actually remove punctuation in Python. We'll ignore the join command for now, but we'll take a look at that again in a second. So this is the character is the thing that we're going to be returning. We don't do anything to the character, we just take in the character. For each character in the sentence, if the character is not in the excluded list. And the excluded list, or the set, is string.punctuation. I think we can actually do it without the set. Let's try that real quick. So for example, if we say, in sentence, if char is not in string dot punctuation, let's try. Okay. Maybe I have to import string. Let me clear that and bring it up to the top again. So when we did that, you can see that we took every character and we checked to see if that character is inside of this string.punctuation thing. What is string.punctuation? It's the list of it's the string of all the punctuation in Python. When you do the double quotes.join, that's how you join all those parts together. So for example, if we took this guy here, character char parts, we say dot join all those char parts, that would join them all into a single string. So you can say, hello, how are you? And then we can actually take that end sentence, and we could go and do our split part there. Yes?
Is the first two, is that supposed to be space?
Where?
Or in front of join char parts?
That's an empty string. So join allows you to join the rest of a list to an existing string. And I just say take the empty string. So for example, if I do this, I can say stuff goes here. You can see how the stuff goes here is joined to each one of those elements. I just didn't want to join any of those elements together like that. Here's the H with the stuff goes here. Here's the E with the stuff goes here. Here's the L for the hello with the stuff goes here. I don't ever use join for anything except for making a new string out of a list like that. So this is actually the easiest one, I think, is just doing this one. Length of v in send.split. That's essentially the idea. Okay, so would it be possible to also get the uppercase version of this? So this would be pretty simple. If I took this guy here and I want to get the uppercase version of each word, I can say v.upper, like so. And then you can see hello, how are you? So if you've ever wanted to uppercase everything inside of this string, or lowercase everything that's given to you, we can also lowercase it. So if you need to do input checking, for example, let's suppose they type in a sentence. Input, in equals input. Type in a sentence. Is that not supposed to, isn't that how we did it before? Apparently in is a keyword. How are you today? Like so. We want to make sure that we can get the lowercase version of all that input in each word. Done. We wanted to be able to strip that question mark off the end. There was the one we were using before on how to strip the question mark off the end. it's very easy to get sets of input data that has been parsed in some way for you. Another cool thing about this is that you can do multiple things at once. Forgot to call it upper. So now I built a list of lists where the first element is lowercase, the second element is the uppercase, and the third element is the length. So I now know multiple pieces of information about each one of those things inside of the sentence that I was looking at before. Any questions about this guy here? So earlier, this is going to be something separate, but let's answer this because it's kind of interesting. Earlier, I mistyped the upper because I didn't call the upper. In Java, this would have been an error. In C, this would have been an error. It said you can't do that. Lua and Python both would have accepted this, but what you get is you get this built-in method upper of string object as the output. What does that mean? For example, built-in method upper of string output. If I was going to save this to a variable A, let's save this to the variable capital A. How do I get, or what do I do to be able to execute this guy here, that built-in method up there? What does that mean? So if I said A of 2, A of 2 is that entire list. It's the list of our built-in method with the length of 3. A of 2. Python is what kind of indexing? Zero-based or one-based? Zero-based. So 2 is actually the third element, or the last element in this case. So it would be, there's that built-in method. Can I call it? Okay. What is that concept called again? Your function pointers. What is this concept here of having this function pointer here? Functions is data, that's part of it, but there's another concept we talked about, Python being something. Python is what? Python 3 is more of this than Python 2? Lazy, right? And so in this case here, hey, I have a function that I have not executed yet, but I could if you wanted me to. Here's the result of a function that I executed. And so you can either execute the functions if you want to or not. You don't have to. All right. The next step with list comprehension. So for example, this guy here, this is the prime example. So this is how you calculate all the primes. Primes x for x in range from 2 to 50. X is not no primes. Here's a list of all the non-primes. Here's an example of how to do prime calculations very quickly. In this case here, the no primes, we're able to use both. We have 4i in some range and 4j in some range. And it does both of them. So it's as if they're nested. You'll get for each I, you'll get for each j, and so on and so back, and so on and so forth. The next step after this, though, is that Python is limited, unless they change it, Python is limited to being a finite input set. That means that the number of input values is finite. For example, this one here, the limit is 50, and it calculated up to 50 of those prime numbers. As we move into Haskell, Haskell is not limited. Haskell has this concept of list comprehensions on infinite strings, or infinite streams is what they call it. You get a stream of numbers that is now infinite. So for example, this is a Haskell expression here. If I take, for example, the number 42, 42 is 42. It is a number. A becomes A. If I take 42 and I add, say, +1 like so, it is 43, the way we expect it to. If I say cycle 42, it's a list to a set of lists. This Haskell interpreter is smart, and it didn't blow up on us, which is nice. Depending upon the Haskell interpreter you get, if you run this on Windows, that cycle command may actually just make your computer non-responsive. It's an infinite list. It's an infinite list of the number 42. Haskell is this idea of take. So for example, I can take some number of things from it. Let's say let x equals cycle 42. No. Not gonna like me to do that. Let me do this. Haskell interpreters allow us to do this let x equal thing, which is unfortunate. Let's try this one. Take 4 cycle 42. Let's see if it'll let me do that. Okay. This interpreter is not giving us a lot of input, a lot of output. It's okay. Haskell is even lazier than Python is, and it only does things that it has to. So what did I say was special about Haskell? It works on numbers, right? But x equals some value. I should be able to say x equals 3. Doesn't have any mutable variables. And so some Haskell interpreters, when let is the keyword that you use to say, hey, let's do this. Let me use a variable x. Some Haskell interpreters will allow you to do that. Say let x equal the value of 3. This Haskell interpreter will not. It'll not let you say the variable x is the value of 3. So up here, what I tried to do is I tried to say, let's take the variable x and have it equal the value of cycle 42, and it wouldn't let me do that. The cycle of 42, however, is a valid Haskell command. It's just this is a list that goes to another set of lists. And when I said take 4 on cycle 42, it's a take function is applied to 3 arguments. And didn't let me finish it off. It says it only has 2. I don't know exactly what that means. Maybe I wanted to do it the other way. Take cycle 42. Let's try that one. The other direction. Not letting me do that. So we'll have to figure out another way to make it take the cycle of 42 and so on and so forth. But so Haskell doesn't allow you to do these assignments. The Haskell interpreter that you can get. So for example, if you search for Haskell interpreters, let's do Windows first. Windows, Haskell. If you go to the download Haskell program platform here, this is the one I would recommend here. What you get is you're going to get a couple of different parts. Let's see if I can actually install this and see what happens here. It's only 194 megabytes. We'll let it go. It'll be done in a couple of seconds. Faster than information. Also comes for OS X and for Linux. You're going to get a couple different parts when you do this. After this finishes installing here, we'll come back and we'll take a look at it. The Haskell interpreter that comes with this installer from Haskell.org does allow you to use the let command, let x equal some value, and it'll allow you to do that. Let's look at an example function, though, in Haskell. So for example, I can say the function f operates on an argument x, and it returns x plus 2. I'm not going to let me do this. Anyways, maybe we have to say let f. We'll let me do that one. So, and notation. All right, I'll have to figure out what's up with that guy there. I've never used this one before. Haskell interpreter. So the Haskell functions. Let me make the screen go away. We'll come back and look at it. Haskell functions take on the form like this. You have your name, your arguments, what to do. So your function body. You can also do list comprehensions in Haskell. The same kind of idea that you're doing list comprehensions in Python, but your lists don't have to be finite. So for example, in Python, we had a finite list. We said 1, 2, 3, 4, for example here. An example of a list in Haskell, you can always return something that is going to be x plus 1, for example, will always be bigger. Haskell list comprehensions are a little bit different than Python list comprehensions, so this is an example of a function declaration. A Haskell list comprehension is going to be this, with your bar in the center, there. This is going to be the function to apply. These guys over here are going to be the source of data, the same way we had before, source of data. And variable declarations. In Python, we said, for example, for v in some list. In Haskell, you're going to use the arrow. So, for example, you would say x in some thing here. You put something there, and then you have whatever function. So, for example, x there. Let's see if that would actually work. It's going to end up very similar looking to something like this, for example, where you have the monkeys function for v and so on and so forth. Over here, it would look almost identical actually, except we use the bar in between the two of them. You can say, for example, monkeys of x, bar x in 1, 2, 3, 4. So the 1, 2, 3, 4 would be the original part. The arrow is the four v in x comes from that.
Less than minus sign.
Yeah. The interpreter's almost finished. There's this website called Learning Haskell, which I'm going to recommend. Right here. You can buy it if you want to, or you can just click read it online for free. And learn you a Haskell for great good. This is a very good introduction into Haskell from other kinds of languages. So for example, if we go to the I'm a list comprehension, here's an example of list comprehensions. Let's make this bigger. We can see that this is essentially the same concept that we did before in the previous one. X times 2. In this case here, we'll just multiply by 2. We could also use the multiply to get the power. This is an example of the if statement. We use a comma instead of saying if, and so the language doesn't have as many parts to it. In the case of when I say parts, it's the syntax for words when you read it. You can do entire expressions inside of the execution part. So for example, here's an if-else statement. If x is less than 10, then you do boom, else bang, and you can do, and those are the two values. X is coming from the string xs, where for odd x's, let's see if this is functional. We can run some of these guys. You're going to get this WinGHCI guy as an example. This is the guy here. So this guy allows us to do things like let x equals 3. If we ask what x is, it's the value of 3. If we cycle 42. No, didn't let me do that. Let me try this one. Maybe it needs me to do this. Nope, I don't know why. I don't know why it's not letting me do cycle. I used cycle before. Here. All right. So, for example, if we wanted to do the monkeys function, monkeys of x equals. What is equal sign? Equals x times 2. So there we go. I'm not particularly proficient in Python, or not Python, Haskell. So there we're going to get the let at monkeys of x equals x times 2. Now I can say, for example, monkeys of 3 is 6. See if I can make that bigger. The other part of this is Haskell is not as uniform as other languages. So for example, the online interpreter didn't let us use the let. Some interpreters that you download won't let you use the let. GHCI, which is what we're using here, WinGHCI, does let you use the let. Other version of Haskell won't, and so if you download and use a different version of Haskell, it won't work like this necessarily, which makes it kind of not the same kind of fun. But now we can do, for example, if we did the monkeys one, monkeys of x for x in the list 1, 2, 3, and 4. 2, 4, 6, 8. So that's the list comprehension we did before. One of the cool things about Python is you can say, okay, let's let the list x equal this list comprehension. We'll have this v plus 1 is going to be, value is going to come from x. That's correct. So in here, when x is the new list that we're generating, the values for the list comprehension of x are going to come from x itself. We're not going to be able to print out x. It's the head of x. What am I doing wrong with that? X of 1. So I'm trying to make because it doesn't have an initial value. Let's try it this way. No, it's not going to. Okay. So I'm trying to. So it's not letting me construct the infinite type t. That's what I was trying to make it do, where x, it becomes the list comprehension of x with the other parts. What if I get rid of the these guys here? All right, I don't know how to do that right. Sorry. So I'm going to refer you to this guy here for the extra credit assignment that we're going to be doing in the that's going to be due with the when we start the final. The final is not going to include any Haskell for you to be doing. Essentially, it's read how to do these things, learn how to do a little bit of the list comprehensions, and take that and get extra credit points for it. Here's an example. Let's do, see there's the cycle. Why doesn't it not let me cycle this, guys? If I take 10, cycle 42. Yeah. Okay. What happens if I cycle the list 42? Oh, there we go. Maybe that's what I was missing before. It was the list before. All right, so that is what it is. Haskell is probably going to be it depends on on what you do. It's going to be one of the less useful languages for most of you. That's why I don't use it very much, obviously, as you can see. However, the concept that it has, the idea of having infinite lists and infinite strings, is important to know. If we do some other kinds of concepts, for example, math concepts, math things. If I have a matrix, if I have that matrix, and I want to do and multiply that by another matrix. How much parallelism can I get? And where's the dependency? How many people don't know how to do this matrix multiply personally? Everybody knows how to do this? Good. Where's the dependency and where's the independency in this multiply?
The rows of the first one have to equal the columns of the second. Or sorry, rows of the first matrix you have to equal the columns.
So the number of rows,
Yeah.
right? So the number of rows here have to equal the number of columns, right? Why? You're right. Okay, so we have to be able to multiply each row for one column, each row item by each column item, right? Is that multiply independent of every other multiply?
No, it's the dot product of the column versus the row goes on to the other side.
So is the multiply independent of the addition? Correct. So for example, when I take 10 times 1 and 13 times 2, doesn't matter which order I do that in. No. But I know that I'm going to be doing 10 times 1 and 13 times 2 there and 16 times 3 as an example. And I'm going to have to do each one of those. I also know I'm going to have to do 11 times 1 and 14 times 2 and 17 times 3. I have to do each one of those multiplies. How many total multiplies are there? I think it's more than that. So it's going to be, no, I think it's less than that. I think it's just n squared. I mean, well, maybe if you say n is the size of one row, then it would be n cubed. But so if we look at the total number of elements here, so for example, if we have 9 elements here, we have to do each one of those. So for example, this guy has to be multiplied by 2 to 3 of those, right? So this first column would be 3 times 9. Would that be true? Is that 3 times 3, 6, 9? Oh no, maybe you're right. 9 times 3. I'm kidding about it. That's a lot of. Anyways, there's a lot of independent calculations we can perform, and if we wrote those all out, we could get 10, 11 times, or 10 times 1, 11 times 2, 12 times 3, etc., etc. We'd be able to write all those out. After we do all of the multiplies independently of each other, what's the next step? What do we need to do? We need to add some of them together, not all of them. But we're going to do some sort of addition. And so, for example, these guys are going to be added together, and the 11s are going to be added, the second column is going to be added together, and the third column is going to be added together after we do our multiply. Is the addition independent of the multiplies? No. So the addition here is dependent upon some set of these multiplies. It's fastest. The way what you have to do when you're looking at your calculations is figure out how to do all the independent steps first, then do all the dependent steps. And if you can figure out how to make the dependent steps independent of each other, so for example, this addition is independent of this multiplied by each one of those rows. So how many steps does this actually take? Does doing this multiply take? Total. If we did this by hand, it would take us lots of steps because we have to do each one of these individually.
Like you made a list of lists that were all the multiplication results. You could do it in 2 steps. Just have them add each of the lists together.
Right. So if we did it as all the multiplies first, and each multiply resulted in a new list element, and then you had the. So for example, I wrote this list here. And you have another set of lists that would get generated here of that list, and then you just sum each of the individual lists inside of them. It would be 2 steps. Now, all of our processors are capable of doing this in 2 steps. Whereas if we wrote a nested for loop, we'd have to take 81 steps, at least. This is an optimization that will allow your code to run that much faster. Yes?
Does Python actually spawn threads to do stuff like this? Or are you using this?
Python does not. Haskell does. So when you're, and that's the tricky part is, we can write this in Python. It doesn't necessarily mean it's going to be multi-threaded or independently viewed. But if you can figure out how to make these lists in Python, then you can start to think about how to do this in terms of Hadoop. So let's suppose 3 by 3 is pretty small. But what kind of things are matrices?
Traffic algorithms.
What would be the main, so they're traffic algorithms, sure.
For determining light patterns and traffic lights in the city.
Sure, I haven't thought about that at all, but yeah. Yeah. What are kind of other kinds of things would be matrices of stuff?
Graphics.
Graphics, so 3D graphics, which is what we usually use graphics cards for. Graphics cards usually have 256 by 256 processors, which means that they're able to do 256 steps simultaneously at a single time. So each one of their instructions is 256 simultaneous steps. And so, for example, here if we had 9 steps, we could do 256 divided by 9 of these multiplies simultaneously on a graphics card. It would take us 2 steps to do that. And then people will spend a lot of money to play games on that. What other kinds of things? That's what, when we talk about graphics cards, the games and stuff, that's what we mean. Yeah. What other kinds of stuff?
Is it in compression algorithms?
Yes, less so than other places though. Compression algorithms typically aren't parallelizable because the data is dependent upon each other. This is also true for encryption algorithms. They're not usually parallelizable.
Well, I was thinking of codecs for video.
Yes, that's a different. Yes. I was thinking like 7-zip or something like that. Yeah. Other things are DNA sequences. So when you talk about looking at human genomes are essentially matrices of numbers that are put together. When you look at folding molecules, so you want to talk about how do you take 2 molecules in chemistry and fold those 2 molecules together. Why do they fold that way? That folding is matrices of numbers multiplied together. When you're looking at simulations, simulation code is oftentimes just massive matrices multiplied together, and you want to be able to do that very quickly. All of these steps are improved using something along these lines, if you're able to do that. I don't have much else today. If you have specific questions, please come and ask me. But we could be done. I will make sure that the homework gets posted for Python. The Haskell one will go up as well, but it's not due until the final. We will take a look at, the final is going to be the 12th, I believe.